Okay, we're going to look at pre-stressed concrete now, just up until lunchtime. So what we're going to cover this time is basically just what Eurocode 1992 does and doesn't say about pre-stressing. I'll just very, very quickly make the distinction between pre-tensioning and post-tensioning. I'm sure everyone knows that, but we'll just do that because the Eurocode covers post-tensioning quite well, because that's mostly what our mainland European friends do a lot of, and it doesn't cover pre-tensioning very well because they do less of that. Then we'll spend a bit of time looking at the maximum allowable stressing loads. That's both during stressing and after transfer of the pre-stressing force. And then we'll spend the rest of this session looking at losses, both short-term and long-term, how we calculate those, and also what SLS stress checks we have to do for pre-stressed concrete. So what does Eurocode 2 cover? Well, most of what we're going to talk about now, if not all, is within section 5.10 of Eurocode 211. And don't be misled that it looks short because it's only a sort of a subsection of a section. Section 5.10 is actually quite a long part of the code. What it deals with is maximum allowable pre-stressing forces, the calculation of pre-stressing losses, and also the treatment of pre-stress both in section design and in the global analysis. What it doesn't cover in section 5.10 is anything to do with the ultimate behaviour. We've basically already covered that. So as I said yesterday, there's no distinction in the Eurocodes between pre-stressed sections and reinforced concrete sections. They're just treated the same way. So it doesn't say anything about bending design or shear design. That's using the rules we've already discussed. And it also doesn't contain any rules, as I mentioned in the session on strut and tie, on the design of the anchorage zones. We have to use the strut and tie rules to do those designs. So just very quickly, pre-tensioning and post-tensioning. When the code is talking about pre-tensioning, it's meaning this sort of situation. It's meaning that the bridge beam has been constructed by, first of all, stressing the strand, the tendons between abutments, then casting the concrete around those strands, and then cropping the strands or transferring the force from the strands to the pre-stressed section. Pretty straightforward stuff. And there's a nice gratuitous picture of a pre-tension beam. And I had to put that into a presentation previously because when I was talking to a German delegate, they didn't know what pre-tension beams were and they'd never seen one. That's what we're up against in the Eurocodes. Post-tensioning, okay, obviously when you see post-tensioning in the Eurocodes, what it means is you've cast things the other way around. We've cast the concrete first with an empty duct there. We've then installed the strands through into the hardened concrete, and then we've stressed the strand once the concrete has reached a suitable strength to do that. And again, another gratuitous picture of a post-tension bridge. So what can we actually stress our pre-stressing up to in pre-tension design and post-tension design? Well, basically there are two clauses within section 5.10 which cover maximum force prior to transfer and the maximum force in the tendons after transfer. And basically the reason why we have to control or limit stresses in reinforcement are typically threefold. First of all, the higher we stress the strand, so the nearer we get to the ultimate tensile strength of the strand, then fairly obviously the bigger the risk there comes of having a tendon failure, which could be quite devastating. If you pull the strand, it snaps and the strands do come flying out of the wedges, and it's a very dangerous operation. So we have to put some practical limit on the upper bound strength, stressing load. Also, as we get towards the ultimate tensile strength, the strand doesn't behave linear elastically anymore, where we start to get some sort of plastic non-linear behavior. And again, we want to try and keep well away from the non-linear region of the stress-strain curve, because otherwise, again, it makes it very difficult to measure the pre-stressing force. Well, not so much measure the pre-stressing force, but to actually check the pre-stressing force by using extensions. It's very difficult to do that if you haven't got linear behavior. And then thirdly, the other reason why we have to limit stressing loads is that the higher we stress the strand, the more unpredictable the relaxation loss becomes. So normally pre-stressing strand, we quote relaxation at 70% of ultimate tensile strength, and that figure is usually quite robust. When you get to 80%, manufacturers will quote relaxation losses, but they become significantly less robust, and they could be actually quite a lot more than that particular figure. Obviously, the higher you go, the more unreliable that figure becomes. So there's another reason why we have to limit the stressing forces. So we look first of all at the maximum force that we're allowed to apply. The Eurocode gives us a simple expression. It just says the maximum force we can apply is the cross-sectional area of a tendon times sigma p max, which is the limiting stress. And there are two limits. We have to satisfy that the lower limit. The first limit is a fraction of the ultimate tensile strength, K1 times FPK, the ultimate tensile strength. And the second limit is K2 times the 0.1% proof stress of the strand. And the recommended values for K1 and K2 in the Eurocode, which the UK National Alliance adopts, are 0.8 and 0.9. And if you take a typical pre-stressing strand, as specified in the N10138, then you'll find the proof stress is normally about 86% of the ultimate tensile strength, which means that the second limit is the one that governs. So that the limit of 0.9 times the 0.1% proof stress is the governing limit. So we cannot stress more than 0.9 times the proof stress. If you prefer thinking in terms of ultimate tensile strength, as I still do, that is equivalent to a maximum stressing force of 77% of ultimate. So that's your upper bound. There is one exception where you can stress higher than that. You can stress to K3 times the 0.1% proof stress, where K3 is 0.95, and that will equate to about 82% of the ultimate tensile strength. But you're only supposed to do that if you have great confidence in the jack equipment that you're going to use, that you can measure the accuracy of the final pre-stressing force to within plus or minus 5%. So by definition, it's not intending that you're using this as a design, because you're not going to know anything about the jacking equipment at that time. This is really intended for the situation where you get out on site and for whatever reason things are not going well, you've got too much friction or something like that, and we need to stress harder to make the design work. In that situation, and if you've got that confidence in the jacking equipment, then you can pull it a little bit harder, but do not use that in the design. So that's the maximum force before tensioning. We've also got to have a maximum or limit on the maximum force after tensioning. Before we get to that, the Eurocode defines the force in the pre-stressing steel as PMT of X. The T is for time, so this is a time-dependent force in the pre-stressing, and the X is a distance along the pre-stressing strand. So it's a general definition of how the pre-stressing force varies spatially and in time along the strand. And the pre-stressing force with time and distance is basically the maximum pre-stressing force that you first stressed it to, minus delta pi, which is the initial elastic short-term losses, minus delta pc plus s plus r, which is the long-term loss from creep plus shrinkage plus relaxation. So short-term, before we've got the creep, shrinkage and relaxation, this is going to be the critical time for checking normally the maximum stress that we've locked into our structure. So we're only interested in looking at PM0 of X, i.e. T equals 0, which is the maximum force we first used minus the initial elastic losses. And in the same way as we have to limit that stress before tensioning, we have to limit it after tensioning. There's a similar expression. It basically says that PM at T equals 0, any position X along the strand must be equal to, or mustn't exceed, basically, the AP, the area of the strand, times another limit, sigma PM naught of X. And this limit is, again, the lower of two limits. It's the lower of K7 times the ultimate tensile strength, or K8 times the 0.1% proof stress. Again, the UK National Alliance has adopted the recommended values of K7 of 0.75 and K8 of 0.85. And that basically, once again, means that the second limit is normally the governing one with normal strands, and it will equate typically to a allowable stress after lock-off of 73.1%. So that's a little bit higher, again, than we were allowed previously in the British Code, where we were allowed 70% basically to be locked into the structure. May not sound very much, but it actually can equate to quite a saving in pre-stressing steel if you've got a big bridge to be able to actually lock in that extra sort of 4% of load. So right, loss calculation. There's nothing new in any of this loss calculation, by the way, as you'd expect, because how many different ways can you calculate the elastic shortening, the sort of friction losses, etc., etc. So you'll find things are very similar to what we did before, but in some ways they're better because we've actually got formulae for most of these situations, whereas in BS500 we just had sort of text descriptions of what we were actually trying to achieve. So this is an unusual scenario in the Eurocodes where we actually have more formulae than we used to have rather than fewer of them. So in terms of the sort of losses generally, the short-term losses, the Eurocode tells us what we have to consider. We have to consider loss from the elastic shortening of the concrete when we stress. We have to consider any short-term relaxation of the pre-stressing strand as well. This really typically only affects pre-tension beams, where if you're making them by stretching the wires first, you can actually get some relaxation just while it's sitting there before you've actually built the concrete around it. But what you're actually getting is some fraction of the long-term relaxation. But it's just something to consider at the start of the design rather than later on. We have to consider losses due to friction. So that might be because we've got a draped tendon in the post-tension bridge, or it might be because we've got deflectors in a pre-tension bridge. Either way, if there's a change in angle, we have to consider that in the design and the losses. And then also if the anchorage equipment that we have, again whether it's in pre-tensioning or post-tensioning, can suffer from some slip as we transfer the force to the concrete, then that needs to be taken into account as well. So post-tensioning, that's normally part of the contractor's standard anchorage equipment, and there'll be some quoted slip when you transfer the force. For pre-tensioning, there will probably be some sort of slip in whatever equipment's being used, but that's the contractor's problem. It's not an issue for the designer. We don't need to worry about that. So when we specify force, we expect the contractor to have factored that out, so we don't need to worry about that. And then long term, as I say, after we cover the short term, long term we have to calculate the losses from creep, shrinkage and relaxation. So if we look at the immediate losses, then this slide is basically just telling you what immediate losses we need to consider for pre-tension beams, and they are basically just the ones I've just talked about, so I won't go through the slide again. We'll just move straight on to the one which is specific to pre-tension beams, or specific in the way that you carry it out, which is the elastic loss of force and that transfer. And you'll find this formula is given to you in the code, and it's just, again, what we've always done. So all it is saying is that transfer, when we transfer the pre-stressing force to the concrete, if that creates at the location of the strands, any position x along the beam, a stress sigma c of x, then we get a loss delta p elastic in each strand equal to the area of the strand times the strain in the concrete, which is sigma c over ECM, times then by the E value of the strand itself. So this is assuming that, correctly for pre-tension beams, that the strand is always bonded to the concrete at every position, and therefore we'll get a unique loss in the pre-stressing at every position along the beam. And sigma c of x there, it's defined as the stress in the concrete adjacent to the tendons at transfer, so that needs to include everything that's actually, all the loads are actually acting on the beam at transfer, so it's not necessarily just the pre-stress, but it will also be the dead load of the beam itself that it's picking up. That simple equation is what's given in the code. What's given in the notes that we've got on the bridges side is a slightly more expanded out version of the same equation, which basically just contains a denominator. And that's just really reflecting the fact that if you just stick with a numerator on top, it's conservative, because as you get the loss progressively coming on from the pre-stressing, the sigma c, which you started with in the first place, is obviously reducing, and therefore the loss itself is reduced from the initial value. So that including the denominator is just a slight sophistication, which for most typical geometries will just shave another sort of 10% or so off the losses. So it may not be worth doing it initially, but if you're struggling with the design, it might be worth going back and revisiting that to get a little bit more force out of your tendons. If we jump onto post-tensioning, then and look at elastic losses, then we have a very similar expression. It looks very similar. We've got a pre-stressing area, we've got an E value for the tendons, we've got a sigma C, which is the stress in the concrete, we've got the E value of the concrete. But we also have a J term there, which I'll explain in a minute. But the other significant factor for post-tension beams is that normally when we're calculating the loss from elastic shortening in post-tension beams, the pre-stress is not bonded to the concrete. So we end up, rather than a whole series of different unique losses along the length of the beam, for post-tensioning we end up normally with one average loss over the whole length of the beam. And therefore, strictly speaking, when we look at delta C, the concrete stress at the level of the tendons, that should be an averaged value along the whole length of the tendon if we want to do it properly. And the worked example in the detailed notes does that, shows you how to do that. In reality, what most people do is just take the worst concrete stress, any position along the tendons, and then use that to calculate the loss everywhere, but that is actually quite conservative. So that's one major difference. The other is this term J, and this is reflecting that with post-tensioning, if you're doing typical span-by-span construction, so you build one span and then stress it all up, and then you probably grout the anchors, then move on to the next span, stress that up. If you're stressing up a block of tendons, let's say 4 tendons on the end of a girder, the first tendon that you install and stress up won't have any elastic loss because you've just pulled it. The concrete's shortened, but you're still pulling it as the concrete's shortened. And once you get to the force you actually want, that's it. You lock it off, so there's no loss. When you come to put the second tendon in, then the same is true of that second tendon, but while you're stressing the second tendon, the first one is getting shorter. So the second tendon causes a loss in the first one, but not in itself. And then consequently, when you do the third one, it causes a loss in the first one and the second one, but not in itself. So what J is doing is it's saying if you've got N tendons in a group, and we consider the stress sigma C from the whole group, we need to take into account that the fact that the last tendon we stress causes an effect in everything, but not in itself. Yeah. So if we only got one tendon, then J becomes N minus 1 naught, and J becomes naught, and therefore that says we have no loss if we've just got the one tendon. If we've got an infinite number of tendons, then J becomes 0.5, or a very large number of tendons, and J becomes 0.5. And for intermediate cases, we obviously get something intermediate to that. I think what we've probably mostly done in the past when we've done post-tension design is we've effectively used J equals 0.5, but without actually ever defining what J is. We've just used half of the force to reflect that progressive loss of tensioning. There's a little more sort of science around what the Eurocode says. Friction losses. Basically, the friction losses, that formula just comes entirely from consideration of statics. So it's the same in the Eurocodes, other than one small definition which is changed. So you'll see that the friction loss there is the maximum stressing force in the cable times 1 minus e to the minus mu, where mu is the friction coefficient. And then we've got in brackets theta plus kx. So we get a loss with angular change, theta, and we get a loss for wobble in the same way as we do in BS 500 with distance x along the cable. But in BS 500, in the exponential, there was no brackets. It just said e to the minus mu theta minus kx. So the very subtle difference is that in here, the k is actually being multiplied by mu. So if you compare wobble factors, wobble values in BS 500 and the Eurocodes, you'll find they differ by a factor of 1 over mu. And that's quite important to note, because a lot of manufacturers' data, if it's been written for BS 500, it doesn't assume that presentation of formula, so the k value it's giving you is not compatible with the definition of k that we've got there. So they'll differ by a factor of 1 over mu, so just be careful with that. Another way of presenting that expression, which I find easier to sort of get my head around in terms of what the forces look like, is just to say that the force at any position along the cable P of x divided by the initial force that we started with is equal to e to the minus mu theta plus kx. And one of the advantages of writing it like that is that the minus mu theta plus kx is a small number. So e to the minus a small number can be linearized into a simpler expression. P of x over P max equals 1 minus mu theta minus mu kx, and that makes it a lot easier to sort of draw out diagrams, if you like, of how the cable force varies along a typical cable. Just before we look at those, the Eurocode gives you some ideas of what values to use for the friction coefficient. That's basically just reproduced in this table. So for different types of wire, cold drawn wire, strands, bars, smooth round bars, and then for different conditions like steel ducts, HDPE ducts, steel ducts have been lubricated, or HDPE ducts have been lubricated, it gives you some ballpark figures that you can do your design with. I would suggest that we don't use those. I would suggest that we do probably what we've been doing in the past when we've done post-tension design, have in mind somebody's system, whether that be VSLs or Fresno or whatever, and then just use those values for that particular system and just quote those as that's what the design's been based on. There's nothing new. I mean, this is only what we would have had to do in BS 500, but just very quickly as an illustration, if we have a simple sort of tendon profile, like the one shown here, which is a bit idealized, having sort of sharp kinks in it. If we have something like that, then we can plot out the cable force due to friction using that simple linear expression. So if we start at the left-hand end of the cable, for the first 4.1 meters, we're basically just going in a straight line. So there's no actual angular change there, but we do have some wobble, equivalent to the wobble that we're going to get over 4.1 meters. So looking at the linear presentation, there's no angular change, but we're going to be descending down at a gradient of mu k. So that's what's happening here. We're setting off on the force diagram an angle of mu k. 4.1 meters along, we have a sudden angular step change of 5.5 degrees. So that's a minus mu theta term, which gives us a step change in the force in the cable. And then for the next leg from 4.1 to 32.5 meters, again, we just have a straight profile. So we have some wobble loss, no friction loss, and we're again descending on a line parallel to the first gradient at an angle of minus mu theta. So it is quite a good way of quickly plotting out the way your force variation is going. And if you've got things which are continuously draped, then I mean you do exactly the same thing. It's just you idealise the continuous drape as a series of kinks. So you end up with a series of sort of gradients and steps, which if you like you can smooth out afterwards. So that's friction loss. Drawing loss, not too much to say about that really. This is sensitive to pre-stress manufacturers' particular systems, and typically the two of the main systems that are about at the moment have draw-ins of 6 millimeters and 12 millimeters. But it's worth recognising that you're not guaranteed to get those, obviously. I mean, if somebody says they're drawing 6 millimeters, it might be naught on site, or it might be 1 millimeter. So it's sometimes worthwhile just checking the sensitivity to draw in, just to make sure you're not going to lock in enormous amounts of force if you get no draw-in at all. And the effect of drawing, it really depends on how long your beam is. So if you've got, again, let's say 6 millimeters of draw-in, if you've got a very, very short beam, then that draw-in loss will work its way back over the full length of the beam and will create a loss over the whole length of the beam. If you've got a very, very long length of beam, then friction will actually stop that 6 millimeters of draw-in going all the way back to the other end of the beam, and it might not have any effect at all at the far end. Just to illustrate what's happening there, if we go back to our very simple diagram, what we drew out before here on first stressing was a force against extension, force against distance diagram, basically. And so if we've got that, the area underneath the curve is actually a measure of the extension, and we can write the extension of the cable initially, basically using the integral here. So if we multiply the force at any position x times its little dx and integrate it up, i.e. the area under the curve, and divide by the pre-stressing strand area and the E-value of the pre-stressing, then we'll get the total extension of the pre-stressing. If we want to find the draw-in loss, or we want to find what draw-in does, then we basically need sort of two bits of information. We first of all need the draw-in loss, so how much extension are we actually going to lose in the pre-stressing. And what we can see here is that this little diagram here, the shaded area, is actually what the strand profile looks like after the draw-in. So we've lost an amount of area that's given by that shaded area, and we again use that integral to equate that area to 6 millimeters. So that's how we can size up the area. The other piece of information we need is that when we get the friction loss, the force along the cable must still obey this basic friction law, but it's inverted the other way around because the force is now bigger at the other end. So what you end up with is a mirrored picture of where you started. So all you do to find that what profile you actually end up with is basically guess a point where the loss goes back to, turn it upside down, calculate what the area is, and if it's not equal to the 6 millimeters, then you shift it in one direction or the other, again mirroring what you've got. Again, there's nothing new here, but this is just the way we sort of see things being used with the Eurocodes. I don't think you haven't got in a handout, but again, if you go onto the Bridges site or you go into the books, then basically example 510.1, the first example in section 510, gives you an example that goes through and calculates all of those short-term losses that we just talked about for a typical sort of draped cable. So that's short-term losses. Long-term losses, we come back to basically needing to work out what the losses are going to be from creep and shrinkage and relaxation. So starting with creep, we've said several times thus far that creep is treated in a more rigorous way in the Eurocodes. So when we want to calculate our creep losses, we need to calculate the creep strain from the expression there we've got up on the screen. So that's basically just saying the creep strain is the elastic strain times a creep factor. And we have to get the creep factor from either from some simple charts in the main body of Eurocode 2 part 1.1, or from some formulae which are in Annex B, if we want a slightly more accurate answer. One thing to note, and I think that the example we'll do after lunch together, or the example we have a crack at after lunch, to give you a bit of a break from me, does actually put us into what's called the nonlinear creep region. What the Eurocode says is if we have under permanent loads so much pre-stress that our stress in the section exceeds 0.45 FCK, then the basic creep factors are not adequate. The creep will actually be bigger than predicted by the phi factor from the simple calculation in Annex B, and we have to calculate an enhanced creep factor for nonlinear creep according to the expression here. And basically that's just taking the basic creep factor and then increasing it exponentially for however much our stress is above 0.45 FCK. So if K sigma is basically the stress divided by the actual applied stress divided by FCK. So if our stress is 0.45 FCK, then the term K sigma minus 0.45 just becomes 0, and we just end up back with the basic creep parameter. But as our stress rises, that exponential kicks in and the creep goes up considerably. So it's not saying that you must not stress your concrete more than 0.45 FCK, but if you go considerably above that, you will pay one hell of a penalty in terms of losses and also the unpredictability of deflections and behaviour. So it's probably a good idea to regard that as something not to go too far above. Shrinkage. We said yesterday that you have to calculate your shrinkage from two components. There's the autogenous shrinkage component, which doesn't involve water moving out of the section, it's just the water being consumed in the hardening reaction. And then we have drying shrinkage, which does involve the water seeping out of the section. And they happen over very different timings. The drying shrinkage happens over the same sort of time period as the creep happens, but the autogenous shrinkage happens over a much shorter period. So whilst when you do your creep calculation, in theory you add the two components together, you do need to take account of the times that you're actually considering. So if you've got something just sitting around doing nothing before you've pre-stressed it, you may find that actually a lot of the autogenous shrinkage has disappeared and it's not actually affecting anything. And so when you come to do your shrinkage calculation, you're only really worrying about the drying shrinkage. So you need to take account of that, or be conservative and just add them together. If you do add them fully together, you'll find they come out quite a bit higher than the previous BS500 figures. So for post-tensioning, we used to consider 200 microstrain, and I think for pre-tensioning, we used to consider 300 microstrain. Well, these numbers often come out sort of 350, something like that, when you add the two together. The last long-term loss we have to look at is relaxation, and this is a little bit different from the approach we had previously. The table at the top right basically identifies the three different types of relaxation class that you can have, and most of our designs these days, if not all, use low relaxation strands. So all that means is if we have a strand stressed to 70% of its ultimate tensile strength at 20 degrees centigrade, and we leave it there for 1,000 hours, then we'll get a relaxation of about 2.5% of the steel, of the force. What we used to do in British practice was we used to just take the loss at 1,000 hours as the loss. So if we had low relaxation strand, we would just use 2.5% as a blanket loss of force on our strand. We can't do that in the Eurocodes because it provides these equations which tell you what the loss is with time. So if we're talking class 2, the low relaxation loss, we have to use the expression for class 2. And that tells us how our stress will reduce with time, but also how it's affected by this parameter mu, which is the initial stressing force divided by the ultimate tensile strength. So clearly the higher we stress initially, the bigger the relaxation loss will become. If you mess around with these, well, it doesn't really take much messing around. If you pick up these equations and you try and get a feel for it, the first thing you probably do, which is the first thing I did when I first saw this equation, was I tried to put in T equals 1,000 hours, mu equals 0.7, and see if I got 2.5%, and you don't. So it doesn't give you enormous confidence. There is something wrong with them. We haven't been able to get to the bottom of what it is, because even the drafters of Eurocode 211 are not completely sure of the background of where these things have come from. It does not work at 1,000 hours. However, when you go to T equals infinity, or the code actually tells you T equals infinity, I think it's 57 years. That's what you have to do if you want the long-term value. It does actually give you something sensible at that value, but for short term, very small t's, it doesn't give you something which equates directly to the 1,000 hours value. And what you'll find is that if you take class 2 normal relaxation strand and you consider the long-term value from that equation, you get something like about 4.3%, or it's just over 4%, so it's more than the 2.5% that we've had previously. But on one of the next slides, you'll see there's a correction which actually brings it back down to almost the 1,000 hours value that we used before. So once we've got all those losses together, there's a formula given to you in the code which tells you what the total loss of force is due to creep, shrinkage, and relaxation. And it's made up of three terms. You've got the shrinkage term, ECS times EP at the top. That's easy to calculate the shrinkage. We've got the loss due to creep. We've calculated our creep factor. We know what the stress is, and we've got the modular ratio. And then the middle term is the loss from relaxation. And that's the figure that I said would be about 4% for a class 2 strand. But you'll see it's multiplied by 0.8 in that equation. And the 0.8 is basically a fudge factor, which just allows for the fact that when we have relaxation in the steel due to relaxation, we've also got a reduction in the forces due to these other effects as well. So we're not, whilst the derivation of those formulae assumes that you've stressed the thing to a fixed force and then it's relaxed, the reality of the situation is other effects are also reducing the pre-stressing force with time, and therefore that also reduces the relaxation loss. And the best way they could think of doing that was just to factor it by 0.8 as a calibration factor. But then that then brings us back to effectively a loss due to relaxation, not really that dissimilar to what we had previously of 2.5% using the row at 1,000 hours. So I think all it shows is actually 20 years ago we were actually quite bright and switched on to these sort of effects and just did something pragmatic. And now we've kind of created a long-winded way of getting back to the same sort of pragmatic answer. If you want to be quick, then you only need to consider the numerator, because this is the same denominator basically I showed you for the short-term elastic relaxation loss. And once again, the denominator is, for most normal sections, it's only going to be about 1.1 or something like that. So you can leave it out, but come back to it if you desperately need to get your losses down. Just very quickly, if you've got composites, the Eurocode doesn't really cover things like what we do day to day. The pretension beams made composite with a deck slab. It's not so good if you, in terms of telling you what to do, if you change the cross-section properties. So, for example, the expression that I showed here has obviously got a unique set of section properties in it. So you end up having to apply the equation sort of twice to different cross sections, which is not ideal. Which is another good reason just to conservatively take the denominator as 1 to save that hassle. Strictly speaking, if we have this situation where we have a pretension beam and then we make it composite, we should calculate our total loss, but then we should apply only that part of the loss that occurs during the time the beam is there without the slab to that cross-section property, and then the remainder of the loss we should actually strictly apply as a tensile force at the level of the pre-stressing to the composite, because that loss is effectively happening on the composite section, not just the pretension beam. I don't think that's actually common practice. I think what most people do is calculate their total long-term loss and then apply it all to the pretension beam. In the example we'll look at after lunch, it does it both ways, and you'll see that actually applying the whole loss to the pretension beam is actually a fair thing to do, because you don't really get a very different answer, to be honest. So again, if you go into the detailed notes, example 5.10.2 gives you the same post-tension beam, and it goes through and calculates all the long-term losses that we've just talked about as an example. I'll just very quickly just mention differential shrinkage and differential temperature now. The calculation of differential shrinkage is really to be done exactly the same way as it was in BS500, same formula, but the total shrinkage that you consider is going to be different. It's not going to be the 200 microstrain or that we had previously. It will be whatever you've built up. But aside from that, it's the same calculation. What we have, which is new, I think, is an explicit treatment of creep redistribution, which is actually, I think, quite useful and quite helpful. And it's catered for by a formula, the one that's up here. What this is saying, if we take a sort of typical example where we come across this problem of having two simply supported beams then joined together, what this is saying is there will be due to creep, there will be a gradual creeping from the as-built condition, i.e. two simply supported spans, towards the condition we'd have if we built the whole thing in one go. And the reason for that, obviously, the beam sags. If this is just no pre-stress here, by the way, just for now, this is just a simply supported reinforced concrete span. If we build two separate spans, they'll sag. Then we join them together, and creep will make it sag a little bit more. But the rotations are now constrained in the two halves at the joint. Or put another way, if you took the support away, it would sag further down with time, and the support will push it back up, thus generating a hogging moment. So the green line is the as-built condition. The white line is what would happen if you just wished it into place all in one go. And what you end up with as a final design with time is the red dashed line, where it's crept from one scenario to the other. So the question remains, how far does it creep from the as-built condition to what you would have got if you built it up in one go? And that's all that this expression here is telling you. It's saying that the shift, where delta S could be a change in bending moment, change in stress, change in shear, it doesn't matter, it applies to the whole stress state. The change in bending moment, let's say, is equal to the bending moment we built it in one go at any location minus the bending moment that we got following the actual construction sequence, times a factor to do with the creep factors, and this is basically the factor that tells you how far you are between the two extremes. And this factor here, phi infinity t naught, is basically the creep factor that we had for the beam to time infinity, given that it was first loaded at t equals t naught. And phi tc comma t naught is basically the amount of creep factor that we would get up to a time c when we made the beam continuous. So this is sometime after first constructing the beam. And then the term on the bottom, phi infinity comma tc, is the amount of creep factor that we have after the beam was made continuous. And chi is another fudge factor to make things work, which has a value of 0.8, sort of relaxation factor. And for typical concretes, what you tend to find is that the creeping effect from the as-built condition to the monolithic condition is around, it goes around 50% to 2/3 of the way. So actually just ignoring the creep redistribution is not a very good picture of how the stress state finally finishes. The thing with creep redistribution is it doesn't matter at all at the ultimate limit state. You can just forget about it. But at the serviceability limit state, that's actually what's going to happen. So if it produces stresses in places and you ignore it, then you will get cracking. The normal situation with pre-tension beams made continuous is exactly the upside down version of this, in that we normally put in far more pre-stress than we have dead load. So rather than creeping downwards, the beam creeps upwards. And therefore, rather than generating a hogging moment at the support, we create a sagging moment at the support. And various people have written papers about the need to put in reinforcement in the soffit, at the bearings, to prevent sort of splitting going on there. So that formula also applies not only sort of span-wise, but it also applies for redistribution within a cross-section as well. So if we have a situation, as we typically have, where we have a pre-tension beam, we get a bit of creep, and then we then put a deck slab on the top of it, exactly the same applies. So we have a general creeping from the way we built it up to the situation we would have if we applied all of the dead load and the pre-stress to the composite section. So what we want to do, if we want to work out these sort of internal redistribution type effects that are going on from creep, we need to build up the stresses that we've actually built up ignoring creep. So this is just the pre-stress applied to the beam and the dead load, giving us a total. But then we want to pretend that we just put all the pre-stressing on the final structure. So it's the pre-stressing and the dead load is now applied to the composite. And we'll get two different stress blocks. We then use exactly the same expression to interpolate how far we are between these two blocks. And the difference between those, the redistribution effect, is this sort of possibly familiarish diagram that you get for creep redistribution if you calculate it. And quite often the creep redistribution is actually relieving to the design, which is why many people don't bother doing it, but it's not always relieving. Okay, just to finish with serviceability, the pre-stressing checks that we need to carry out. Having got our stress after all, our force after all losses, PM of time and X, then we need to use that in our actual design of the section. And the Eurocode defines an upper and a lower value, or bound value of the pre-stressing force. So we take the value we just calculated, and we should consider an upper bound value by multiplying by R sup and a lower bound value by multiplying by R inf. The recommended values of those are 10% more and 10% less than we've calculated. But in the UK, we've just set both values equal to 1.0 because we really couldn't be bothered to do the check twice at the upper limit and the lower limit. Quite often it's hard enough to get your design to work with one unique value of pre-stress, and the last thing you want to do is try and get it to work with two values of pre-stress, and there hasn't really been any historical need to consider upper and lower bound values because our structures have survived without cracking to pieces. In terms of compression, these limits are really just the same as Jessica would have mentioned in the previous section. At transfer, we have to limit our stresses to 0.6 times FCK. But if the fabricator or manufacturer of the precast beams can demonstrate that he does this regularly and never has any problem, then he's allowed to actually increase the stress at transfer up to 0.7 times FCK. And then there's just a reminder here that although this isn't a limit in compression, if we increase our compressive stress on the section to more than 0.45 FCK, then we do need to consider this nonlinear creep, which could be quite onerous. In terms of tension at transfer, there isn't actually any specific provision in the Eurocode. So whilst BS 500 used to say you could have a tensile stress of 1 megapascal during transfer, there isn't actually anything at all as a limit. So As a pragmatic approach, you could use 1 megapascal of tension, because we know that works from the past, and since he didn't say anything about it. Or arguably, we should just follow the normal rules on crack widths and decompression. So depending on the environment, we either need to check decompression under the just forces at transfer, or we need to check crack widths. It's a lot simpler just to actually check transfer to 1 megapascal like we used to do, to be honest. One thing that you'll notice, I think it will come up in a minute, that sometimes we have to check decompression under different load combinations. When the Eurocode talks about decompression, it doesn't mean no tension. It actually means what's shown in this picture here. It means that you shouldn't have any tension within 100 millimeters of the pre-stressing strand. So quite often, if you haven't got 100 millimeters of cover, or you've got less than 100 millimeters of cover, then decompression does mean no tension. But if your strand or duct is further inside, then all you have to achieve is 100 millimeters of good sound on cracked concrete around the duct. So that's a nice little get out, but in practice I think most people will carry on treating decompression as no tension, because what we've generated here is now a sort of cracked section property, and we're trying to check stresses, on a cracked section property, which is not so easy as just using the gross section properties we've done before. So it might help you, but probably we won't be taking advantage of it generally. So these are basically what we have to comply with. We've already seen these for RC. If we have reinforced concrete, or basically external tendons, not bonded tendons, then for external pre-stress we just treat that as a piece of reinforced concrete with some axial forces on it, and therefore the crack width requirements are just the same as they would be for reinforced concrete. If we've got bonded tendons, then we have a different set of rules, and they're slightly more onerous for bonded tendons, which is just really people being a little bit more worried about the consequences of corroding tendons than they are about the consequences of corroding reinforcement. So as we come down the table to more onerous conditions, we have more onerous requirements. So if we have XC3, for example, which might be bridge deck under waterproofing, then we only have to check that our crack widths under the frequent load combination are less than 0.2 millimeters. But we also have to check this little superscript D is also saying that as well as checking crack widths, we must check decompression under the quasi-permanent combination. If we go down to XDs, so we've got chlorides, then we're a little bit more onerous because we have to now check under the frequent load combination that we have no cracks. Basically, we've satisfied that decompression check. And there's another little clause which the National Annex has added in here, 0.2, and we've got this superscript E, and this is just actually saying that there may be parts of the cross section where we don't need to check for decompression because the tendons are too far away, for example, from the surface, and in those areas we should still make sure that the crack widths aren't bigger than 0.2 times E. So that's basically like your surface zone. And in terms of the reinforcement and the stresses that we can use, we just have exactly the same table that we use. So if we've got 0.2 millimeter crack width requirement, then our reinforcement has to be strained to different limits to what it would have been allowed to be strained to for a 0.3 millimeter crack width. And then finally, once in service, we've got the same limiting stresses ready for concrete and reinforcement that we have for reinforced concrete. So concrete compressive stress is less than 0.6 times FCK, unless you haven't got either XD, XF or XS, in which case you don't have to check compressive stresses at all. Reinforcement needs to be limited to 0.8 times ultimate tensile strength, and pre-stressing has to be limited to 0.75 times ultimate tensile strength under the characteristic combination.